Hello, and welcome to the Explaining Rust Analyzer series, where we try to understand how Rust Analyzer works one subsystem at a time. Last time, on our first lecture, we looked at the Rust Analyzer repository as a whole, which major process consists of, how to run the test, how to work with repository, what is our code style, that sort of stuff. Today, we will start diving into the actual logic Rust Analyzer. Specifically, we will be looking at the virtual file system subsystem of Rust Analyzer. This is a good target for the first real dive in because it is relatively isolated. It doesn't depend much on other bits of Rust Analyzer, and at the same time, it shows a lot of important considerations about how data is handled in Rust Analyzer. Basically, by understanding why we need virtual file system, you will understand a lot about the overall data flow in Rust Analyzer, and understanding how the data moves in the program is the main step towards understanding the program as a whole. Because, well, data is much more important than algorithms which are used to process it. Let's start. So we have two VFS-related crates. I can't type. We have two VFS-related crates, VFS and VFS Notify. But we will start with another one with paths. So the paths crate is really simple. It defines absolute path type and also abs path type. And correspondingly rel path and rel path. All four types are wrappers around the corresponding STD paths. Why do we need this? So, like, what we do here basically is we track, is this path absolute property of a path at compile time? And the reason for that has to do with how Rust Analyzer thinks about your project. When you're writing command line utility, like a compiler, it typically works in a batch mode where you give it some input or some directory, run it, and get the result. And for such utilities, a notion of current working directory relative to which every relative path is interpreted makes sense. It makes much easier for the user to specify inputs as relative paths and that sort of stuff. Basically, you work only on one item at a time, and that item usually lies inside the current working directory. Rust Analyzer is different. Rust Analyzer is not a batch program, it is a long-lived process. And it also thinks about many projects at a time. For example, one possible use case for Rust Analyzer is just to open every project you have on your hard drive and let the Rust Analyzer analyze cross-references between the projects. So, for example, if there are two crates which are not parts, a part of the same workspace, but one crate uses the other crate, Rust Analyzer should be able to find usages of one crate inside the other. So if you have like two routes you watch, you don't really have a reasonable concept of what is the current working directory, because there is like one project in project directory, another project in temporary directory, and they kind of like both equivalent. That's why inside Rust Analyzer, using current working directory is generally a mistake. We always want to work in a context of specific cargo project, specific cargo toml, and use path relatives to that. That's why when we get an STD path from the operating system, from like some API, we usually try to immediately make it from relative path into an absolute path. And we usually try to make it an absolute path relative to something which isn't our current working directory. For example, if there is some relative path in the configuration file, we tend to use the path of the configuration file as the anchor. We actually had a lot of, well, not a lot of, but quite a few bugs in Rust Analyzer where we accidentally sneaked in dependency on the current working directory of rationalizer process itself, and that was the motivation for writing this crate. As a kind of spoiler, we actually will see a lot more of custom path types in Rust Analyzer today, but paths is the first one. So let's now look at the virtual file system crate. The first question is, why do we at all need a virtual file system? Why can't we just use stdfs read text or something like that? So let me type small example. Why can't we just do something like this inside Rust Analyzer? It's curious. It's kind of like a two-purpose question. One is like the question for this question, and another is the question mark. I guess I need to add more punctuation here. Yeah. So there are several issues with that. The most important one is repeatable read problem. Again, when you're writing a batch tool like a compiler, you typically read the file only once and then use it. In something like Rust Analyzer, you probably want to read file several times, at least because user can actually modify the file and you need to somehow learn about changes about this file. And that means that generally you kind of have this situation at runtime where you read twice from the same file, and operating system doesn't provide any guarantees about the semantics of repeated reads of the same file. The result might be the same, but the result might be different. And for example, if you just accidentally read the file twice and assume that it is the same, but then it is different, you can get an inconsistency. When you write something like an ID, it's kind of useful to realize that the stuff is always consistent and it doesn't change under your feet until you specifically ask it to. So kind of like the first source of needing to repeat reads is just that files change. There's another reason to repeat reads, is that Rust Analyzer forgets things. What do I mean here? Basically, Rust Analyzer wants, unlike a compiler, Rust Analyzer works with all the crates at the same time. And that means that it needs to keep a lot more information than just the compiler about the whole crates. To give a simple example, if you're writing a library and then you ask for find usages of some symbol in this library, you actually want to find usages in siblings of this library as well. And that means that, yeah, kind of like, bad example. Yeah, well, let's make it less hand wavy. Let's say we have something like vec new, and we want to find the usages of this symbol. So, and it's a new function that probably are going to take a while. I'm actually wondering if we can support find usages from the standard library. Anyway, the ideal behavior here is that you find the usages of vec new across the whole crate graph. You find them in the standard library, you find them in crates.io libraries you find them in your own code. And that means that Rust Analyzer actually, okay, yeah, we found them all. And yes, as you see, this actually works. This took a while because our search isn't specifically optimized, but we actually find the usages of vec new in pretty much everything which exists. And like at the end, there are like some usages in our code. And yeah, to for example, find a usage in this zip decoder buffered or something, Rust analyzer actually needs to parse and understand the code inside functions in this crate. So when Rust uses a crate, it looks only at metadata about the crate, only at its public functions and that sort of stuff. But for Rust analyzer, we need to know everything. That means that we, in general, use more memory than the compiler. Like significantly more memory, because compiler works with a single crate over time and we work like with all the crates. And that means that we want to optimize memory usage a lot. And one trick here is that we want to forbid information which we no longer use. Specifically, when we open this file, we obviously need to type check and otherwise process the body of this function. Because, for example, I want to go to definition with unwrap call here. But normally, we actually are not looking at the files in the dependencies. So ideally, the behavior we want here is that when you first go to this file, you read it from disk, parse it, and analyze it. But when we go back to this file and when we close the other file, we want to forget this information. But then we want to go back there, maybe someday, and then we need to reread it again. Yeah, I guess that's a lot of words just to say that Rust analyzer has derived data, and it has ability to forget derived data and recompute it on demand. And this ability is useful to reduce memory, and it crucially depends on ability to exactly reproduce the inputs. Because if, for example, that file changed, then derived data would also be different, and we will get some internal inconsistencies. If, for example, if you remembered offsets in that file somewhere and then reparse it, and then offsets no longer make sense, and you get internal inconsistency, panic, and that sort of stuff. So yeah, basically we need repeatable read, and that's why we need virtual file system. Another reason why we want to have a virtual file system is that file paths are actually OS-specific thing. Paths on Windows work differently than paths on Linux and work differently than paths on macOS. And Rust standard library generally tries to expose the paths as is. It wants to give maximum flexibility to the calling code to write programs which behave exactly as programs written in C using native APIs of a platform. In Rust analyzer, we actually specifically do not want this. We want the definition of a Rust language to be independent of a particular file system, of a particular operating system where the Rust code resides. So we want to make not only like cross-platform type, which can represent a path on any platform, but we actually want to go further. We want to have a platform agnostic path type, a path type which doesn't care at all about what platform it uses. For example, it could just enforce that all the paths are UTF-8, and UTF-8 paths are a common denominator between different operating systems, so that could work. Finally, so one is like repeatable read. First one is platform agnostic paths. And finally, the third reason is that we want to support multiple file systems. What the hell it is? So this is like a hypothetical use case. This is, you aren't gonna need it probably, but I like to architecture Rust analyzer to account for some crazy future use cases. And the use case here is that I want it to be possible to write Rust code on, say, Windows machine, but analyze it using a Rust analyzer which runs on a remote server on, say, Linux machine. And the problem here is that if you use, like, foo.rs absolute path on Windows. Although yeah, it probably should be something like this. I haven't used Windows paths for a while. Yeah, basically, you can have this on Windows machine, and then you need to be able to work with this path on Linux machine. Similarly, if this Linux server serves two different Linux clients, they both can have this /foo path, but that actually refers to different files on these two different clients. Basically, I don't want to encode in Rust Analyzer that paths are the paths on the host machine. I want the paths to be just some like logical entity pointing somewhere and have very clear mapping between actual host file system and the way Rust Analyzer thinks about it. Because Rust Analyzer really wants to think about file system as just a nice tree of text files without symlinks, without hard links, without like any sort of platform specific different model. Okay, so let's see how it works. First, we have file ID type. And file ID is something you will be seeing a lot in various bits of Rust Analyzer, and it basically identifies a specific file in a virtual file system. Internally, it is just an index. And if you look at the database, you see that the actual data is stored in a flat array. And this is actually one of the few places where I kind of like how Rust Analyzer internal data structures works. Note that for each file, we actually store an option because we explicitly want to represent a fact that a specific file doesn't exist on the file system, that the file was deleted or something like that. To map from file IDs to actual file paths, we use this pair of functions, and yeah, they basically do the mapping. They do it using the interner inside, and the interner is a relatively simple thing. Just, I wonder. Yeah, sorry, I'm kind of wondering about mutability here because, yeah. So yeah, internal interns stuff. To intern stuff, you need to mutate internal, so you need exclusive access to it. Here, we see that we have only shared access. So this functions only works for file which file system actually seen before. And the question is, so how do new file IDs are assigned? Because when we create file system, it is empty. It doesn't have any kind of file ID. So when we ask a path for a file ID for a path, we will just get none because there is no such path. Okay, so yeah. This function, setFileContents, actually adds data to the file system and also assigns an ID to the virtual file path. So you see, then this function takes a path, then it allocates file ID, and then it uses this file ID to store the data in this giant vector. Okay, let's get back to the interner. It is just your usual simple 20 lines internal, nothing fancy here. Why do we need file IDs? Why don't we just identify files with paths? Well, there are two reasons for that. One is file IDs are stored a lot, and it's kind of nice if they are compact and just 32 integers and not arbitrary length strings. So that's the first motivation. And the second motivation is that, and that's actually also a motivation for having virtual file system paths and not just standard paths as well, is that I want it to be really, really hard to get from a file ID to some related file in Rust Analyzer. in the guts of Rustinizer. Basically, I want all the accesses to pass through a virtual file system so that it is impossible to accidentally read file from disk and break the repeatable read property. Okay, so I guess we covered file IDs. We covered how they are converted to virtual file paths. Now let's see. Yeah, let's probably actually see what a virtual file path is, because we haven't seen that, I believe. Yep, so first of all, virtual file system, I would just call it VFS path. A VFS path is an opaque type. It obviously has some representation, but this representation isn't exported. And as you see, it provides a platform-agnostic API. For example, you can only join STRs to path. You cannot join with arbitrary file system path. It also is impossible to extract a file system path from a VFS path. Like, some VFS paths do correspond to file system paths, but not all of them. That's why this conversion is failable. Similarly, there's like some modification functions, and again, they all encode UTF-8 assumption, and they all explicitly erase everything file system specific, except this encode function, which we will look into a little bit later. And let's understand how it is represented. Yeah, so there is no magic. Internally, one way to represent virtual file system path is by just using operating system path, like usual spavbuf. So here is it. But another case is just so-called virtual path. And this ties back to my talk about different file systems. So these two variants actually exist on separate file systems. This variant is from actual physical file system. This one is from in-memory file system. And we use such virtual paths when writing tests for Rust Analyzer, so that we don't use some dummy /tmp/something paths in tests, but have first-class support in VFS to create an in-memory file system. And yeah, they just implement the required APIs. Okay. So now, let's see how virtual file system is modified. An interesting thing to realize is that this VFS struct doesn't actually have the capability to watch files or to read files. Probably a better name for this would actually be a VFS snapshot, although it isn't a snapshot. The way you populate VFS is by explicitly calling set file contents, which, as it takes option for a contents, also can delete files. So VFS does not create files itself. It is the user of the VFS who must tell it what contents does it have. And note that every time we call this method, we actually record this change into the changes array. And changes array just records the changes. It records what file changed and was it created, modified, or deleted. We then have a method to take these changes. So the idea here is that the caller has some VFS which doesn't have any changes to it. Then it calls set file contents in a row for some changes they have. And then they get back the array of changes, and they can understand what actually was invalidated. So for example, yeah, not really example, but like, why do we need this at all? We need this to react to changes to the files. So for example, if I switch branches, then many files on a file system will change. What will happen then is that although files on the file system will be different, the data in the VFS would actually reflect the state of the file system before those changes. Then we will get a bunch of notifications from operating systems that, hey, those files are now different. We will reread these files in bulk and update the virtual file system in bulk. Then we will see which actual files were changed. And for each crate which actually had changed files, we will invalidate the caches or something like that. Basically, you kind of like, I guess that's another important high-level thing. So if you think about evolution of virtual file system, it is a series of a snapshot. Because in the steady state, VFS is just a snapshot which gives you a repeatable read. When you apply a bulk of changes to that, and you get a new snapshot. So VFS is a snapshot in a single point of time, and then a list of changed files is a div between two snapshots. So if a file system doesn't actually load files from disk, who does it? It is done by the entity called VFS loader. The task of a loader, well, the loader has two tasks. First, it needs to be able to read files from disk, or maybe not from disk. It is an abstract data type, so it isn't tied to a particular file system implementation. And the second task is that it needs to watch a file system for changes and emit events when it noticed that something outside of Rust Analyzer edited files on disk. Well, that's not correct thing to say. Basically, in Rust Analyzer, we never actually touch files ourselves. So all the edits come to Rust Analyzer as notifications about something changed outside. So let's look at the loader API. The core thing that loader has is config. And what config does is it describes the section of a file system this loader is responsible for. You don't want to load every file on your hard drive into your virtual file system. You want to load only files inside your projects and files inside cargo registry. And this set of files is what is described by config. So config contains a list of entries, and each entry is either a flat set of files or a description of a directory of files on the hard drive. Where directory is sort of like gitignore, but very simple. It contains a list of paths to include, a list of paths to exclude from inclusions, and a list of extensions to actually watch for in these directories. So yeah, that's kind of like, basically this is path to bool predicate which tells if a specific file belongs to this config. And by the way, that's like important thing. The VFS works on virtual file system paths, while the loader, it interacts with the real file system, so it works with real file paths. Then we have a watch config, and watch selects subsystem of entries to set up file watches for them. So when you typically use Rust Analyzer, you want to watch for files in the current projects because you modify them, but you probably don't want to watch for files in the standard library or in the cargo registry because you assume that those files are just immutable. Of course, if they are mutated, you will miss those notifications. But on the other hand, if you don't watch for them, you save system resources. Finally, there is this interesting version field here, again, rationalizer exists in time, and there is no single config for the loader. Config changes over time, and a version is basically an incrementing counter which says which config it is. So handle is the handle to this concurrent entity which watches and loads files. You can create handle using yeah, it's complicated. Why this is not so simple? Yeah, I've already said the word concurrent, so I need to explain a bit about concurrency here. Yeah, so yeah, we want to watch files we want to watch file system, and we want to load files from it, and this takes time, and this also requires system calls. So we want for this activity to happen concurrently with rationalizer processing our code. We want to highlight syntax of a specific file on one thread, and then on another thread we want to notice that something changed, and then later get notified about it and re-highlight the file. That's why this is called handle, and that's why the creation method called spawn rather than new. The idea here is that thing spawns some thread or some epoll loop or something which watches for changes. And when the changes happens, it will just send this change over these callbacks. So sender here is basically a callback. You could have used a channel here, but a callback is more general because you can turn any channel into box DNFN, but it's not possible to do in the opposite direction. If you hardcode, say, crossbeam channel here, you won't be able to turn it into a flume channel without spawning an extra friend to do the conversion. Anyway, so basically this creates a new loader, and the loader will send messages to this channel once it finds that something has changed in the file system. You also can instruct the handle to set the config, and again, everything happens over time. Everything happens concurrently. So the semantics here is that the old config is completely forgotten, and a new config is installed. And a semantics here is that once a new config is installed, the handle should actually go and actively traverse all the directories in the config and create the initial snapshot in the file system of the file system. So basically, the loading happens eagerly here. And once it started processing the new files from the config, it will start sending messages. The basic message is loaded, which says that a specific path, which says that a specific set of files was processed. And the process means that we know that the contents of the specific file is now this. Again, we use option here because we want to say something like the file was deleted. So for example, if you create a loader and set it config, it first will return you files where these contents is always some. But then, for example, you delete some file. What loader will do is that it will notice that the file is deleted and then send an event for a path which was deleted using none here. Loading a bunch of files is actually a pretty slow operation, so it would be good to have some kind of progress indication there, and that's why loader sometimes sends progress messages telling how much of a current config it has processed. And to attach progress message to the correct config, we need to have a version here. Note that we don't have a config version here. That is because we ultimately feed the data from loader to the VFS, and the VFS actually doesn't care that it contains only the files we are specifically interested in. It is okay to store a superset of the files in the virtual file system. Basically, not storing all the files at all is just an optimization to safe processing. It is not incorrect to store more files. Anyway, another two things loader has is invalidate, which asks handle to asynchronously reload a specific file. Actually, I don't remember why do we need this. Are we actually using it? Oh, right, yeah. We use it, and we use it actually for a very interesting use case. So this loader deals only with files on disk. But when you actually type in an IDE, if you make changes to the file, like type something, these changes do not actually hit the disk until you press the save button. So we have an extra layer which attaches a set of in-memory files on top of virtual file system. And while a file is this in-memory state, we don't actually care about VFS changes to this file, because even if file system says that the file has changed on disk, if the editor still has the same in-memory representation, we don't care about that. However, once the file is saved to disk, we want to reload its true contents there. And that's where the IDE calls this invalidate method. If you look here, yep, this happens exactly on the did close event from the LSP when we remove a document from a set of in-memory documents and then ask VFS to reload this file. Finally, load sync is to reload files synchronously on the current thread. And this is like some kind of an API smell, actually. Like, this shouldn't exist. We always should go via asynchronous loading of files. We should request virtual file system to get the file, and that get the actual file from the message. But we actually haven't got to fixing this yet. Actually, kind of like these two methods are doing the same thing. The only reason for this is that this method blocks until the file is loaded, while this method just schedules invalidation of this file, and the result, the actual option of VEC of bytes, will be loaded via this sender in this message. Anyway, so what we have here is just some code to conveniently describes entries. Like, for example, yep, if base is a path to a local cargo package, then we want to include every Rust file inside this directory, but we want to ignore .git and target because they are big and they are actually irrelevant. And that's what happens here. Okay. Entry. Yeah, and a subset entry is basically a predicate. So here is this predicate reified, asking about where it contains file or contains directory. And actually, I'm not sure why we need two functions here. Like, why do we need to know if this path represents a file or a directory? But yeah, we actually do need this distinction. Probably need to read source code to understand that. Okay, as I've said, this handle is actually object safe, and it is not implemented in this VFS crate, so that we can have many different implementations. And the reason for that is that watching for file changes isn't actually a solved problem. Every operating system has some APIs to watch for files, but they are all kind of like incompatible and broken. And they are broken in a very specific sense, when you use watching APIs, you want to have some kind of a guarantee. Specifically, you want to have a guarantee that an event is never ever lost. So if you set up a watch for a directory, and then a lot of events happened inside the directory, you should get a bunch of notifications. And there might be duplicate notifications, there may be delayed notifications, stuff like that. However, once the changes to the directory stopped, you need to have a guarantee that the stream of events will also actually stop, and that eventually you will get all events for all the changes that happened there. That's kind of like hand-wavy way to describe it, but basically the raw file system API make it very difficult to actually get this guarantee. And they, my understanding is, at least I'm not an expert in watching file systems, but they basically require you as a user of this API to maintain some non-trivial state to actually get back this guarantee. And that's why, at least again, my understanding might be wrong, the architecture of the most advanced file watching library today, Watchman, is really curious. So Watchman, the file watching server used by Facebook, isn't actually a library. It is a binary. It is a binary which runs a global service, a global process, which maintains this state, which allows it to reconstruct from the set of events sent by operating system, a set of events which actually has these guarantees of completeness. Basically, it serves as a polyfill for a mission operating system API. And then the actual Watchman client library just connects to that. We don't use Watchman right now, but in theory, it shouldn't be too hard to plug Watchman as a separate implementation of this handle. What we actually use instead is the Notify library-based implementation, and that's why we have VFS Notify crate. So it defines a Notify handle struct and then implements loader handle for this Notify handle struct. And again, this is all pretty concurrent. I guess the concurrency section would be a separate video, because this one is getting way too long. But yeah, there's nothing too super complicated and super fancy here. Basically, we try to get Notify API and actually make it in the same more declarative shape we have for loader, because again, kind of like what I want as a user of a file system library is to say, hey, library, here is a predicate about the paths on the file system, and they want to be notified about all the changes to the paths which match this predicate. Notify gives you a more raw, more low-level interface, so there is a bit of futzing here to actually get this more declarative style out of it. Yeah. Anyway, going back to the virtual file system, I guess even not going back, but maybe it's time to look at how this is tied together. This will be very confusing because Rationalizer main loop is pretty complicated and again deserves a separate video, but just to give some weight to my words about VFS and VFS loader, let's look at how this is made. So Rationalizer main loop processes events, and one of those events is actually the virtual file system event, which contains this message we looked before. And so when we get this event that some files are changed, we actually take the VFS and we modify these VFS contents. Unless, as I've said, the current file is overlaid by in-memory documents. Then after and yes, note that we just kind of like just set the file text, which I remind you appends change to the set of pending changes. I guess this actually should have been called pending changes, because like the semantics of a VFS is that once you start calling set file contents, you should not actually use the VFS until you took the changes and processes them and reacted to their reacted to the changes. Basically, a correct implementation of set file contents would be to not modify the file contents in place, but instead to stuff this for later application and then do actual modification only in the take changes method. Again, this actually would be beneficial to coalesce changes to the same file. Anyway, so we call this set file contents and accumulate changes. Then separately, okay, I guess it is slightly more complicated than that. Yeah, so we set file contents and we also okay, yeah. We also has this yeah, I'm looking for a place of code where we actually react to the changes. Yes, here it is. Oh, I guess we don't actually try to detect if there are right changes or not, or no changes on this event loop turn. We actually always act as if there are changes and probably do nothing if the set of changes is empty. This is, yes, this is on the top level. Yeah. So here finally, at the end of the event loop turn, we take the set of changed files and then we react to these changes. I guess I will go into the details of what happens there later. Okay, let's go back to VFS. It's actually taken way longer than I anticipated. I'm wondering if I should cut this video into two or not. Probably not. Probably makes sense to just complete everything else, because I think we only now have two things which we haven't covered. Those are anchored paths and file set. Well, let's start from anchored paths because they are simple. And again, just as I've said on the start, there are like many paths. There are like absolute paths, there are virtual file system paths, and now there are anchored paths. So what an anchored path is? It again has to do with the notion of many file systems. So recall that example where the Rust analyzer runs on the server, and there are two clients with different file systems which ask the server to process files. And let's say that one of those clients has a code like this. A module with a path attribute which points to absolute file, which points to an absolute path. Well, if this file exists on both our clients, it actually points to different /main.rs on different machines. And that's why in virtual file system, the notion of a file path of an absolute file path doesn't make sense. Virtual file system consists of several disjoint file systems, and you cannot point across those file systems. And that's why even absolute paths are relative. Specifically, the anchored path contains a file ID where we originally found the path, and the path is string. And I assume there is some API to actually resolve this to something useful. Yes, I guess, yeah. I guess the way to go from anchored path to an actual path is to first convert this file ID to a VFS path. And then call join on that. And if the path is actually an absolute path, then it will manufacture an absolute path pointing to the same file system. Again, not sure about the specific details here. I might have lied to you. But yeah, the idea is that we want to deal with this problem given that there are actually many file systems. Finally, file set. File set is an interesting concept. Broadly, it is similar to the config we saw for the VFS loader. The config in the VFS loader specified the predicate on the physical files. What file set is well, let's actually start from a file set config. Yeah. What file set config is, it is a, yeah, that's actually no single thing which corresponds to the predicate. Anyway, yeah, basically, this thing is like config but for virtual file systems. In other words, it allows us to take a virtual file system and split it into disjoint chunks so that every file on virtual file system belongs exactly to one chunk. And why do we want this thing at all? So the idea here is that we create a specific file set for each crate so that files which comprise the crate belong to a single file set, and files from different crates belong to different file sets. Well, why do you actually want this? The example is simple. So this file uses a couple of libraries. It uses like FST by BirdSushi, which is like absolutely amazing library. I highly recommend reading its documentation to learn more about finite state machines. And it uses Rusty hash. And let's say we do something here. Let's say we change like the signature of this function to return an option. So yeah, this is a public function. Its signature changed, so something might have changed on the call side. Now the question, or rather kind of like an observation. Obviously, when we type in this file, we don't need to reanalyze FST and Rusty hash crates because they could not have changed due to changes in the library. But understanding why they could have not changed is actually different, is actually difficult. And it's not actually completely true that it's impossible for those files to change. Suppose that FST crate actually includes something like this. It just like tries to include random file. Well, this random file, despite the fact that this source code of the crate lives in the cargo registry, it actually can physically point to some file in my local projects directory. And it is conceivable that changes to my local files can actually affect creates IO dependencies. So to be kind of like super duper correct, we actually need to reanalyze all criteria dependencies, but we obviously don't want to do that. And that's why we want file sets. File sets are a way for us to very specifically say and explain why this change cannot happen. Basically, every crate has a file set. And we only need to recompute information about the crate when some file changed, if this file is belonging, if this file belongs to the crate's file set. So the reason why we don't need to reanalyze FST on this change is because file set for this crate and file set for FST are different. And so we just noticed that when we process changes and reuse caches for FST. Now, that is not necessarily the best way to do it. Because, yeah, let me start from maybe the other angle. So another property that FST has is that it allows you to upfront calculate file set has allows you to upfront calculate the superset of files the crate might depend on. Basically, you have a file set before you start analyzing the crate, so you can just go and read all those files ahead, and then know that crate would not be accessing any other files because, well, it only has access to its file set. Another way to do this is to sort of construct a file set on the fly, is to start analyzing the crate and start walking the tree of modules and record dynamically which files this crate actually tried to look at. And then you can, like, using this dynamic information, you can actually understand that, hey, you don't need to recompute FST from this file change. So again, two approaches. You either say upfront which file can or cannot affect the crate, or you compute this lazily when analyzing the crate. We went with a upfront approach for two reasons. First, it was just simpler to implement. Again, the code for watching file system is pretty scary and pretty buggy and pretty hard to maintain, so we wanted to keep it simple. If you want to add laziness there, so that you only want to set up a watch when you actually look at the file, then that becomes even more scary. The second reason for that is that if you go with a lazy route, you can only know about a file if you actually try to use it. And for example, if I now go and create random.rs file, okay, file. If I create random.rs file here, then this file won't be attached to the module tree. And in a lazy file system, we wouldn't actually even know that this file exists because nothing tries to load it. In a file set setup, we actually know upfront that all the Rust file in this directory belong to Rust analyzer crates, so we get an ability to look into this file. Again, it's not something which is impossible to add to a lazy model, but it's just we went with eager model from the start. Okay, so let's take a look how this works. So file set config describes a set of file sets, and this is a predicate. This is a thing which takes a path and returns which specific file set it belongs to. You create file set config from file set builder, and you specify a file set basically as just a set of prefixes. so that all the paths under either of these roots considered to belong to this specific file set. Why do we need a set of files here? Well, that's because of various cargo shenanigans. So, for example, if you have a crate.io crate, then its source code lives inside cargo registry. However, this crate might have a build.res which has some code generation. And the generated code from build.res goes to the target directory in your project. So the actual source code for that crate consists of two different disjoint file sets. Of one file set which consists of two disjoint directories. One directory inside cargo registry in .cargo registry git something something, and another inside your target directory. So yeah, that's like complicated. Anyway, you start with file set config builder. You add as many file sets as you like, and then you call build and you get file set config. And then with a file set config, you can actually ask to partition virtual file system into file sets and get back a file set. And the file set, it's basically just a set of file IDs, but for some reason, which I don't really remember now, it also needs to remember the actual paths to these file IDs. And partition is pretty easy. So we just take all the files which are there in virtual file system. We classify this file and we insert this file to a specific file set. Question. How do we know we need to run partition? So partition takes like the whole file system and repartitions it. The problem here is that if you do this on every change, then well, that is kind of slow. So we actually call this partitioning if we have file system changes. And we have file system changes if the change we get from a file system, from the VFS, has a change kind which affects the path that the file is created or deleted and not just modified. So every time you create a file in the editor, then Rust Analyzer runs this partition function, which processes every file on the VFS. Again, this is not really optimal. Ideally, you would want to just incrementally update the partitioning, but actually this is a pretty rare operation and it's not too bad to do it on every file creation or deletion. Actually, I think at one point we accidentally did this on every modification and it wasn't too bad, but we've since optimized that. Yeah, one important note here though is that throughout the file system we support batching. So even if you look at this message, you see that there is no such thing as a single event. Files are loaded in bulk. So even if there are many file system modifications, usually it will get coalesced to only one event and only one partition will happen to process all the changes. Okay, I guess this is, it looks like it's like almost an hour and a half now, but this is probably everything I had to say about virtual file system. So again, to sum up, why do we even need here? Why do we even need this? Yeah, I guess I forgot to actually say anything about like the main operation. The main operation of a file system, of course, is to get the current contents of a file by a file ID. Anyway, to sum up, we need a virtual file system because we want to maintain consistent snapshots. We want to maintain this state changes over time thing. And the way we want to do this is we want to have discrete time. We want to model changes as a series of discrete snapshots, where every snapshot is, well, it's a snapshot, it's reliable. You can like use it and it doesn't change underneath you. Between each two snapshots, we want to get a diff of what changed between them. Note that we don't need to use literally a diff. We don't need to be able to take one snapshot, apply a diff to it, and get another snapshot. We need to have only notifications about what things might have changed. We need to know only which files might have changed. We don't need to know the exact changes. And of course, it's okay if we overestimate this, if we say that some file has changed while it didn't change in fact, because, well, we'll just do some extra work, but the result will be the same. And yeah, this like VFS provides this evolution of snapshots over time. It also plugs into file system API. It plugs into file watching to actually allowing collecting the changes from the file system. And it also tries to isolate operating system specific paths from the rest of the Rust analyzer. The bottom line here, if you are just using file system and not looking at its implementation, is that you have a file ID. And file ID identifies a file in the Rust analyzer, and you can get the text of a file. But it is explicitly, deliberately hard to convert this identifier to a path on the file system, because you shouldn't do that. You should treat files as opaque things. Okay. I guess that's it. See you next time. Bye.